Hey guys, we're going to look at practice problem number 8, and this one's good. It starts with a paragraph length response, which is going to be the second problem on your AP test this year. This is a circuit problem, so we're still kind of in that electricity realm. And so you've got these two circuits, and they're configured in slightly different ways, whereas here you got B and C, they're in series, and then these two are in parallel with D. Over here you take C and you make it its own branch, so you've now got a parallel part right here, and then these three are in series with A. A couple of things about circuits. I always say that batteries are dumb. Batteries really don't know what they're connected to. They just know that there's a certain potential here, right? And there's a certain drop. And so your battery thinks that it's essentially connected to just one thing, right? These two are in series and they're in parallel with D, and so really all three of these are acting as if they're one bulb that's in series with A. And so the battery thinks it's just plugged into one thing. And so when we work problems, we may have to the first thing is resolve these circuits, whereas we have to start and we basically we have to figure out each little piece. It's sort of like a puzzle. We have to say, well, these are in series, so we'll add them up, and then those two would be in parallel, so we'll add them up, and then you have A, and all of these guys are really just in series, and we add them up, and we can figure out total current and things like this. But anyway, for this problem, they're asking us, well, if you have it wired like this versus like this, then is A and D brighter here or is it brighter here? And you have to write a paragraph length response explaining this. You have to support your claims with physics principles using physics language, concepts, things like this. And so what happens is we need to just talk about what happens when things are in series versus parallel. Okay, make myself big for a second. So here's my board. In a series circuit, you just add up resistors or bulbs, whatever. So the more things you have in your circuit, the more total resistance you have. And if you have more R, you're going to have less current with the same amount of voltage. So when we look at, make myself small, when we look at this circuit right here, right, these two are in series, which are in parallel with those two. So what happens here is these two are in series. You actually have, you would add these up, R1 plus R2. That would give you more resistance here, which means you'll have more total resistance for the whole circuit. Okay. Now, in parallel, resistors, you still add them up, but it's the reciprocal of 1, it's 1 over R1 plus 1 over R2 plus 1 over R3. And I always say that parallel circuits are creepy because what this implies, what this means is that the more resistors you plug in, total resistance actually goes down because it's 1 over. And it's very, very strange. So this is odd. What happens is the more you have in parallel, your total R goes down. And if your total R goes down, your total current will go up. That's a thing. Okay. And this is why things that are wired in parallel, you know, like all the lights in a room, right? They're all nice and bright. You can add more lights and they're still nice and bright. It's really weird. So what's going to happen here? Well, you have higher resistance here because you have this little series part here. Higher resistance here, right? And if you have higher resistance, you have lower current. Whereas over here, you have these three guys that are in parallel, so that means that you have lower resistance. You have higher overall current. So if this A versus that A, this A is going to be brighter versus this one because you have lower resistance here. I talk about voltage in class as, I actually talk about it in terms of pizza. You might remember this. You know, if I say in class that if I order pizza for the whole room, then, you know, pizzas arrive and we all start eating. And what happens is y'all get on your phones and tell your friends, and then what happens is people show up to the room. Magically, they appear, and they want pizza as well. And so the problem is that if more people show up to the room, then everyone's slice of pizza gets smaller and smaller. And so this is how voltage works as far as the circuit goes. These two circuits are essentially just series circuits. You have A in series with the combination of those three. And here, for this circuit, you have A in series, with the combination of those three. So you have two series circuits here. Now what happens is that you get current coming out of your battery, and then it's got to come back in. So A here sees the total current in both of these circuits. All those electrons are going to pass by A. So A is going to be brighter than those other guys. Okay. What I say is that the drop here, A has the biggest drop. In other words, it's going to get the most amount of pizza, and then whatever's left over is going to be shared by these guys. Right. So this whole analogy really just works for series circuits. When you talk about parallel, it kind of breaks down a bit. But anyway, this is a thing. All right, so we already said that A is going to be brighter in this circuit because there's less overall resistance. So there'll be more current. Now, when you talk about the fact that when you have more current or more voltage will give you a brighter bulb. The brightness of the bulbs is electrical power, electrical work done per unit time. So if you have more current, then you'll have a brighter bulb. So A here will be brighter than the A there. More resistance here, less here. And what about D? So the way D works is you have greater resistance here, right? Got less resistance here. Now strangely, even though you have less resistance here, that also means you're going to have less voltage in those branches versus these two branches. And so it turns out that D will be dimmer than it is here. And this is a little hard to understand, so I made some circuits with these bulbs. So this is like circuit 1 here. Alright, got D here, there's A is nice and bright. And so here's D. D actually has a voltage of 3.6 volts when it's hooked up like this. It's in parallel with those guys are in series. And then I made the other one. So here's A, here's D, right? And so here they are in parallel, and there's actually less voltage in each of these branches. Interestingly enough, even though there's less resistance, there's less potential. And the reason is because this sucker is brighter. This sucker is getting more pizza. The drop here is bigger than it is in this circuit. Let's see, what is this? 5.4. 6.75. So you get a bigger drop here. 6.75 versus 5.4. And so what happens is there's less left over for these guys, less pizza, right? And so this D here is actually less bright than this sucker is for this circuit. So that's kind of a crash course here as far as how these circuits go. Alright guys, for this next part, kind of a lab-based thing. So a student has a circuit like this. They think that the battery has an internal resistance that is non-negligible. Batteries do have internal resistance that we talked about in class. So if you buy a 12-volt battery, it's really not 12 volts. It's going to be more than that, because when you hook it up to a circuit, you have a little bit of resistance internally as far as the battery goes. So what the student does is they measure the voltage of the battery when it's not connected, and it's 9 volts. So that's your total. That's best, that's without being hooked up. So that's a maximum. And then they put the voltmeter across, and they hook it all up and put a voltmeter across one of these two suckers and figure out that the voltage is 4 volts across this guy right here. So what we can do is we can figure out, okay, knowing that our voltage drop here is 4 volts and there's 20 ohms of resistance, we can figure out the total current going through there, right? Voltage drop is IR, so we can figure out what I is. I is V over R. And V was 4 volts and R was 20 ohms. Then current will be 0.2 amps. So there's 0.2 amps of current total. That's total current, because whatever comes out of this side has got to go back into the other side. So they're both seeing 0.2 amps. Okay, now as far as your battery goes, you can look at the battery as your total voltage source, right? And you can use Ohm's law here. Okay, so if your total battery voltage maximum it possibly can do is 9 volts, then what is the total resistance going to be, right? Well, I was 0.2 amps. R total is adding up all the R's. So you have this R, you have that R, and then whatever this mystery R is within internally in the battery. So 20 plus 20 is 40 because that's in series, plus whatever your internal R is. I divide both sides by 0.2, and that would give me 45 is equal to 40 plus R. This R is that internal R, and so that R must be 5 ohms of internal resistance. Alright guys, for this last part they give you sort of a complex circuit where you've got a capacitor, a resistor, a bulb, and a switch. The bulb and the resistor have about the same resistance. So they close the switch and leave it closed for a long time. So what's going to happen here, when you close the switch, you now have 2 branches that the current can go through. Go through branch 1 or go through branch 2. Both branches are connected to either side of your battery. And they want to know what happens to the brightness of this bulb here. Well, this is parallel. Both branches are connected to both sides of your battery, so they should both get the same voltage. The brightness of your battery shouldn't change. What will happen is you will get some current going through this branch over here, and this capacitor will charge. And at some point, and when it gets fully charged, you won't get any more current there. But the voltages of the 2 branches are the same, so this bulb shouldn't change as far as what it's doing.